we'll talk about some general constructions of submodules. So what do I mean by that? Suppose I have a R module M. So let me say R is a ring, M is an R module. Again, that means left R module. Now, here's one thing we can do. Suppose you take a subset. So this is suppose. So here's the first general sorts of construction that one can make. Suppose S is a subset of M. Okay, no further properties, just a subset of M. Then we can define something called the submodule generated by S. So this is called the submodule of M generated by S. So let's give this notation, angled bracket S, which is the following. It's the collection of all the following elements. So I look at summation, let's call it alpha I xi, I goes from 1 to n, where n is 0 or more, alpha i's come from my ring R and xi's come from my set S. Okay. So this is of course, well, what is this? This is all finite linear combinations, if you will. So this thing here, what I call alpha I xi, is the sort of the scalar multiplication that's given because M is a module over the ring R. Okay, so the submodule is just all what we would call linear combinations, finite linear combinations of elements of S, and this is sort of what you would call a span in a vector space. Okay. Now observe that so it's easy to check that this is in fact a submodule. So here's the following fact: S is actually a submodule, because I mean the submodule generated by S, this set here on the right hand side is closed under addition, and because you add two such terms, you again get another linear combination, and if you multiply such a linear combination on the left by some element of the ring, you just get some other set of scalars, some coefficients in front, that's all. So this is a submodule. The other little thing to check or note is that when I say n greater than or equal to 0, so there is this one vacuous case which also we are taking into account if you wish, which is if you put n equal to 0, then it's an empty sum, so we think of that as just the element 0. Okay, now so I should just say that if in my definition, if I take n equal to 0, so this is just some little care about vacuous definition and so on. I mean, you can ignore it. N equal to 0 gives rise to the empty linear combination, and the empty linear combination is defined to be 0. Okay, now so we have defined the submodule generated by a set. If your ambient module is actually a vector space over a field K, then given a set S, the submodule generated by S is just what you would call the subspace generated by S. Okay, so that's the first general construction. The second general construction is, suppose I give you M, which is an R module, and if I give you a collection, so and suppose I give you a collection of submodules, so Mi I belongs to I. So this is some indexing set. I give you a finite or infinite collection, is a collection of submodules. So collection of submodules of M. Then we can form what's called their sum. So this is another submodule. It's called the sum of Mi I belongs to I. This is defined as follows. I take the union of all the mi's. Okay, now this is just some subset of my ambient module, and I take the submodule generated by this union. Okay, so I've just defined in definition 1, I've told you what the submodule generated by a set is. So I just applied that definition. Okay, so this is called the sum of mi's. It's called the sum of the submodules. That's the definition. Again, it's a submodule because it's the submodule generated by a set. So here's a little exercise. Show that the elements of the sum look like the following, or prove the following equality, that the set of the sum mi comprises precisely the set of elements of the following kind. They look like finite sums. So this is I belonging to I, but I want the sum to be finite. So mi should be 0 for all but finitely many I, for all but finitely many I in I. Okay, and mi's belong to capital Mi for all I. So it's finitely supported sums, if you wish, or finite sums of elements from each Mi. So prove that these two are the same. So these two definitions, if you will, so what we gave as the definition and this alternative description are actually the same set. Okay, so that's an easy verification. So let's do another example here. So if I take R to be the ring of integers, and if I just take two submodules to be, say, 2z, by which I mean all the even numbers, and I take the submodule 3z, which is all the odd numbers. Okay, so the ring is z and the module is also z here. So I'm taking the ring thought of as a module over itself. So of course submodules, as we saw before, are just ideals. So I take the even numbers and the odd and the multiples of 3. They are both submodules here, and it's interesting to ask what's the sum of these two guys. And here's the exercise. Prove that the sum of these two submodules is in fact the whole module set. Okay, and more generally, if you have, so here's more generally, so you can prove this using either of the two descriptions. So more generally, if I take submodules of z, which are all of the following kind, various multiples, so let di's be integers which are at least 2. So if I have a let's say a finite collection of submodules, so this is I goes from 1 to some r. So I take these multiples of d1, multiples of d2, and so on, then their sum, so this is a submodule of z, I equals 1 to r. Show that this is nothing but dz. It's again a submodule of the same kind, where d is nothing but the GCD of all these numbers. Okay, so again this is something which is maybe something you've seen before, but just put in the language of submodules other than ideals. Okay, so that's the second general construction, which is sums, and the third construction is of submodules is intersections. So if I take an arbitrary collection as before, so if mi's are a collection, so this is a collection of submodules of m, then I can talk about their intersection of mi, which is just the set of all elements which belong to all of them. The usual definition, I belongs to I mi, is also a submodule. Okay, and again the verification is more or less straightforward, so I'll just leave that to you.